Perfect. So today I want to present to you about the zero-knowledge app Chain Thesis. I'm Raphael. I'm co-founder at Protokit. And yeah, let's get started. So first, covering all the topic of app chains is that we want to scale up and make blockchains more efficient. So we have here the kind of a condensed version of the evolution of blockchains. And so first it started in 2008 and then the early 2010s by monolithic layer ones. So that's basically Bitcoin and Ethereum. And so after they were invented, they got used by a lot of users and they were bottlenecked because they didn't have an unlimited transaction throughput. And through that, they were slow, got expensive, and yeah. So the first approach to fix that was to scale up the layer ones themselves. These were done through multiple things. There were, for example, the block size wars in Bitcoin. There were forks of Ethereum, like Binance Smart Chain, which increased the block size. And there were different approaches like sharding the execution environment itself, which then also didn't really go further than the exploration phase. So the whole thought process then shifted to general purpose layer 2s, where they're basically you try to move some computation off chain that you then in the end settle again to a layer 1 to receive some nice security guarantees from the underlying layer 1. And so basically there are two types of this. There are optimistic ones and zero knowledge based ones. The optimistic ones, they rely on something called fraud proofs. So in that system, we kind of rely on the rollup to firstly assume that everything is correct, and in case something is not correct, we create something that's called a fraud proof that we then use to resolve the fraud and get the chain back into a functioning state. And compared to that, we have zero knowledge rollups that rely on validity proofs. So they do zero knowledge snarks or starks that attest to the correction of the execution that happened off chain. But this is also, in our opinion, not the final stage of the architecture, because in this scenario, you only kind of replicate the same monolithic model to a larger scale. So you can make 100 monolithic chains. But we think there's a better solution, and we think this is app chains. So first, let's get into the app chain thesis. So what are app chains? Like the thesis as a general basically wants to say that as every protocol that is built on a blockchain wants to scale, they will eventually seek to deploy as sovereign chains that would give them full control of the protocol. So what does this mean? So as a protocol scales, the thesis says that they want to opt for an architecture that allows them to create the most customizable and versatile protocol that they can build. And as protocols grow, app chains become more feasible. So we have a few examples already in the ecosystems. The most prominent one probably is Cosmos. There's also Polkadot, which is already out there for a few years, and most recently ZK-Sync hyperchains, and really recently actually Polygon CDKs. And we've also already seen a few apps that go for the app chain approach. DYDX has, as long as I can remember, been an app chain. They went also through different phases, and with the most recent version, they also utilized the Cosmos SDK, and Uniswap also published some research about them considering going for an uni-chain, app chain, thesis-based model in the long run. All right, so what are the main benefits of app chains? Customization, that's probably one of the biggest ones. You can, for example, through app chains, you can do things like custom transaction ordering, which is important, for example, for order matching. In, I don't know, order book-based DEXs, for example, you can build stuff like that apart from that. You can very easily implement multi-asset transaction fees. CK-Sync, for example, does that. You don't have a native token. You want to be able to pay fees in any asset you like, basically, and the protocol then, in the end, swaps them for you through app chain-powered logic in the end. And also, in app chains, you don't need to adhere to a general virtual machine, like for example, an EVM. You can optimize or customize your VM to your needs. So that leads, obviously, to cost saving, especially in the CK context. Yes. And also, you have a customizable use experience to security trade-off. So in every chain, you have to mostly decide between, do you want to go for a very nice user experience, or do you want to have maximum security properties? They mostly don't coincide with each other, so you have to go either one route or make a trade-off. So through app chains, you have more possibility. The spectrum gets bigger because you can choose a custom consensus. You are not really constrained by any model that's out there. You can just invent your own or use any one of those that are available to you. And also, you can really customize your block size and block time. That also gives you the nicest properties for your users, obviously given the constraints that you are operating in. Like, for example, the proof system is mostly a bottleneck that limits the block size and the block time. So that's something that goes into that. Another big component that actually was discovered by Uniswap was that you can do more granular value accrual. So in Uniswap, there was the case that their users, or the protocol had three major sources of revenue. That LP fees, so basically all the fees that go to the liquidity providers during swaps. Then there were the transaction costs that they had to give to Ethereum, and there was MEV. And so building something on app chains gives you complete control over that. So for example, your liquidity providers can at the same time become validators in the chain. So they get all the transaction fees, which again brings value to your token holders or your stakeholders in general. And yeah, so MEV resistance is also a big part of that. You can customize your app chain to become more resistant. Obviously, you can't remove MEV completely, but you can keep the good MEV because there's actually MEV that is valuable for the protocol. Like for example, arbitrage is very important to keep the price on all pools you have in your system consistent. And there's bad MEV, like for example, sandwiching. So you can get into that if you want. Awesome, but obviously there are challenges. So the biggest challenge at the moment is composability. So in a general purpose system, in any layer 1, in any layer 2 at the moment, you can just compose with other applications by just calling their functions through smart contracts, for example. That's not so easy in app chains. Like, it's a really, really hard challenge to create a framework that allows you to interact with other protocols that live on other chains, because obviously they're separate systems. Coming with that is liquidity fragmentation. Because you have separate systems and they can't communicate with each other limitlessly, you need to have separate liquidity for separate app chains. And that's a bad thing, because bigger liquidity leads to better user experience. And your validator set directly depends on the value of your app. So that means that also the security is directly influenced by how valuable or important your protocol is. As soon as your protocol isn't as valuable anymore, it becomes easier to attack. All right, so now I want to go through some architectures of app chains and how you can leverage them and grow them. And basically we want to create an architecture in the end that satisfies us and gives us the best guarantees. So the first one is sovereign app chains. Sovereign app chains, for example, are stuff built by Cosmos. So sovereign app chains allow you to be in full control of their own consensus, their own security, and their own separate validator set, as already mentioned. So they can really choose freely from them. They can be a centralized sequencer, or you can go through a fully decentralized validator network. But sovereign app chains have a few key drawbacks. As I already mentioned, their economical security is directly dependent on their own token. And successful attacks, if they happen, can be catastrophic. So there's no way to effectively recover a successful attack without going through social measures, which is something we don't want. We always want to be able to recover through technological measures. All right, so this is a diagram of how they can look. You have an app-specific chain in this case, not an L2, that's a mistake from my side. And they do interop by communicating directly with each other, not going through some intermediary layer, but they do it directly. So we choose to go a different route. We want to have app chains as rollups. So this is a table published by Vitalik, and it shows basically 3 different kinds of rollups. You have a disconnected system at the bottom, that's a separate chain, basically a sovereign rollup, a sovereign app chain, sorry. And for that to work, you have to trust a limited set of validators to behave honestly. But the benefit is that it's very cheap. A layer above that, you have validiums that basically leverage either CK snarks or optimistic systems that settle onto an layer 1. And the nice thing about that is that data or assets can be lost, but they cannot be stolen. So the validator cannot behave dishonest, but they can, for example, censor or have liveness failures. And the best guarantees that we can achieve is through a full rollup that uses CK snarks on optimistic model, and additionally to that achieves data availability, so then in case the sequencer or the layer 2 network goes offline, everyone, like the network can be recovered by anyone and they can exit the system safely. Awesome, so going back to the current landscape and especially like looking at composability this time, we have Cosmos. Their main drawback is isolated economical security, as I already said, until they launch something that's called interchain security, which allows them to tap into a shared security network for different app chains. Then with Polkadot, with Substrate. So here it's not CK native, so it was invented 7 years ago. CK didn't exist back then. So they invented a mechanism for the chain to validate something they call parachains, which are basically app chains. And they only do this by selecting a subset of the validators and trusting them to verify correctly and attest to the correctness of the block. And then you have Celestia, which came out pretty recently, or launched the mainnet. But Celestia is only half of a solution because it's only a data layer, a data availability layer for sovereign app chains. So going to app chains as app rollups. So we again have the same properties that sovereign app chains have, maintaining our own consensus, security, and our separate validator set. But additionally, we now have 2 duties that we need to fulfill. We need to firstly settle on a layer 1 that we can do either through optimistics or CK snarks, and we have to ensure data availability. And so for data availability is basically a problem that you need to publish all the data that goes into computing the rollups next state, and everyone needs to be able to reconstruct it in order to recover from liveness failures. And so there are 2 options for data availability. You can do it through the layer 1, which is basically how it's done today. Rollups just post their data onto the Ethereum network, for example, through call data, and that way everyone can observe it and recover. The second option, which is in development by many projects at the moment, is building a separate data availability layer that give you tooling to generate data validity proofs that you can then use for verification on the layer 1, and through that get guarantees. This has the big benefit that it's more cost effective and versatile than doing it on layer 1. All right, but obviously there are problems. Again, fragment and decentralization, because every app chain rollup will have a separate validator set again. So there is a real risk for centralization and monopolies to emerge, especially as the app chains grow, because it gets more expensive to compute. And we still have the limited composability problem. And it actually gets worse in comparison to the sovereign app chains, because in sovereign app chains, how composability works is by relying on finality, which mostly is very good because they can achieve instant finality through BFT-style consensus. But rollups don't generally have the property, because they only get final after the settlement in the layer 1 is confirmed or gets final, so that can take a long time, mostly a few hours. And yeah, through that again comes fragmented liquidity. So this is how that can look graphically. So we have 3 different options here. We have on the left our general purpose rollup, where every DApp lives inside the rollup. Then we have our app-specific layer 2s, which all settle independently to the layer 1. And then on the third option is building them as layer 3s, which gives us better UX, but in this case you have to be very, very careful about your security guarantees, because they can get really bad really fast. Awesome. How can zero knowledge help with app chains? So we have seen that composability is a very big challenge, and most interop protocols have either weak guarantees or they need certain preconditions to be met. Like I've already said, IBC, which is used in Cosmos, needs finality, which is good for Cosmos because Tendermint or their BFT-style consensus is instantly final. Then, for example, we have CKSync Hyperchange. They need 7 full communication verification steps in order for the interop to work, which again gives us bad UX, takes a long time, is very expensive. And we can leverage the property of CK proofs that they are succinct and recursive to fulfill or to achieve better guarantees by using a succinct settlement. And we will come to that back later and see how that goes. All right, so now we've seen that we already decoupled the data availability from the main stack. So why not do the same with sequencing? So that leads us to our proposed architecture, which are using shared sequences. So what are shared sequences? The idea is basically that you have a program or you have a protocol, and at the moment building and sequencing are the same thing. So you have one actor that does the whole process for you, and we want to separate out the sequencing, which is basically ordering of transactions. And so what does that actually give us? It gives us better decentralization, because this process is a very permissionless and stateless process. So doing that doesn't require a lot of hardware. It's not difficult to join, so a lot of people can. And actually also becomes economically really viable really fast. But that also gives us the possibility to use this shared sequencing as a composability layer to build interchain communication. And that is done because shared sequencing gives us atomicity for interchain communication if all those app chains use their shared sequencer. So again, they act as an atomicity gadget for all connected app chains. Obviously the requirement being that the app chain has to use that shared sequencer. It facilitates the composability between app chains, and it's really easy to participate. So that again leads to a high degree of decentralization. So this is how they can look like. Again, for reference, the left one is the general purpose with just standard DApps. And now we have this kind of 3-pillared system where every app chain goes through 3 phases that can actually happen in parallel. The first is the shared sequencing. So every layer 2 submits their transactions to a shared sequencer, which sequences them and commits to that sequence, to that order of transaction and the atomicity of it on the layer 1. After that, basically the result of all app chains, the execution result, is fixed because it's a deterministic state machine, so we can rely on it to always yield the same result. So all that's left is basically execution and settlement. So that is what the layer 2 does after that. It publishes the data on the data availability system. That, again, gives us a data availability proof and also mostly communicates with the layer 1. And then, after doing that, we can settle. The nice thing about this is that after we sequence, everything is already kind of considered final because we have committed to the order of the transaction on the layer 1. So we can just simulate or basically run or compute the state machine that is every app-specific layer 2 and arrive at the same result every time. So that is the reason why we can do that. All right, so we've talked a lot about steps and a lot about settlements. So what layer do we choose for settlements? We at Protokit, we chose Mina. Why did we do that? Biggest part is because it has native proof verification. So every transaction in Mina is a proof. So your settlement effectively is only a normal transaction. It's really easy and also very cheap to settle because proof verification is native. And it actually allows us to build really easy tooling because a rollup will not require huge complicated verification logic on some non-CK native chain. It can just use the already built ones in Mina. Also, Mina is succinct. That means it always has a constant size. The whole blockchain can be verified through one single proof, which is super powerful for light clients. So you, as a user, can verify your state in any app chain that you want through one single proof. You just need to have the data. And it has integrated data availability through sequence state and events. That obviously is a bit limited since it's a layer 1 and not a dedicated data availability system, but you can use this for upgrading your Validium to a rollup really easily. All right, so now we want to show you Protokit, which is our framework for building such app-specific layer 2s. So we built this framework for developers to easily build their own app chain and to settle them on Mina. It's a TypeScript-based framework. It uses O1.js under the hood, so you can use your favorite tooling. You can, the learning curve is very low. You can start and learn it really easily. And everything, zero knowledge is basically abstracted away. So the thing you're building really closely resembles the architectures that you're familiar with. So it's not another CK EVM. We use a custom-tailored CK VM that is really, really bare bones, but allows for the most flexibility, but is also very efficient in the end, which is important since we prove everything. We use a hybrid execution model, so we combine both off and on-chain execution. You can use on-chain for parallel stuff, for your normal application logic, and then you can use off-chain computation in case you need privacy and other features like that. It's customizable and modular. We've built it in a way that you can switch out any component you want. You want a different mempool, just write one and plug it in, it works. You want different APIs, just switch them. You want different data availability, just switch them. And again, we have a very developer-friendly SDK. That was the most important aspect that we looked at during development. And yeah. Awesome. So we have engineered Protokit from the ground up to support all the things concerning app chains that I talked to you about in the last 20 minutes. And so we support decentralized sequencing, shared sequencers, modular data availability, so you can switch out any data availability system you want. And we also built it in the mind of interoperability and composability. Keep in mind, that's on our roadmap. So we are planning to build that, and we've engineered everything so that we can build it easily. It's not just available just yet. And the purpose of Protokit is to basically coordinate and compile all of those components and settle your app chain on a base layer using CK proofs, in our case Kimchi. And yeah, by the way, it's also base layer agnostic. So any layer 1 that can verify Kimchi proofs is suitable for it. Awesome, so you can start building with Protokit today. So everything is running. You can try it out on protokit.dev and visit our Twitter. And yeah, if any questions, I'm happy to answer them. Thank you.
Yes, we can have a question. And do we have any question? Yes, we have over there.
Hello. I want to ask the differentiator between a big and one rollup and a shared sequencer, because from my understanding, the whole shared sequencers should also share the virtual machine, which means that there is a big rollup and connects within the all app chains. So I really can't understand the differentiator between a big general purpose rollup and a shared sequencer network.
Yeah, sure. So the idea of the shared sequencer is to decouple the sequencing from execution, like absolutely. So what you actually do, you just get a list of transactions, and the only purpose of the shared sequencer is to order them and to compose them into an order that then can be executed. So it's completely execution agnostic, so it also doesn't need the app chains or the rollups logic or anything compared to that. It just adheres to a standardized format that every rollup will implement, and after that it doesn't really care what the app chain or the rollup actually does.